Today we're going to look at strategies for testing a series for convergence. So in your packets there's this lovely flowchart, and it's a great resource to have next to you as we look at the next couple of examples. But basically it goes from easiest to hardest, and we always want to start by testing for divergence. Then we look for things that are really familiar, our geometric or p-series. Alternating, if we see that plus or minus action happening, we have a couple of different ways to do that. And then after that, we are going to try either the ratio, comparison, or integrals. Okay, so, and you could also have the root test, but again, that's not tested on the AP exam, and that's looking for if something is overpowered. So, first one up for examples for today. And again, as I had just said, I'm going to start by looking at testing for divergence first because it's quick, and if it diverges, then I don't have to go any further. So we're testing to make sure that our sequence values approach 0. Okay, so I'm doing the limit as n approaches infinity of these terms, and this one comes out as 1/2. That coming out as 1/2 tells me that this series, so while the sequence approaches 1/2, the series, or the sum of all the terms of the sequence, will diverge. Okay, so this is that testing for divergence. We test that. If this comes out as 0, it means that it could converge, but it might also still diverge. Anything other than 0 will automatically diverge. So the test for divergence can't confirm that something's convergent. It can only just eliminate divergence. Next one, I've got here things to the power of n. And you might notice on this that I actually have multiple things to the power of n. As I see this, I would split it into two separate for a moment. So you have 2 to the n over 6 to the n plus 3 to the n over 6 to the n, which gives me 1/3 to the n plus 1/2 to the n. And this is all on the sigma. And by properties of sigmas, I can actually write this as 1/3 to the n plus the sigma of 1/2 to the n. So that's 1. Let's start. Oops. So this happens to not be 1, but 2 geometric series. Okay, and you can see these are going to converge because my r is between -1 and 1, or absolute value of r is less than 1. Okay, so looking for a geometric series is a great strategy because we can tell right away whether it will converge or diverge based on that r value. Next type. Okay, notice here I have like 1 over, or a constant over, a power of n. This particular one, I have some fractional exponents, but I really have just n to the 11/5 or 2.2. So this is a p series. I know this one will converge because my p is greater than 1. So as again you saw in here, we always check for geometric and p series before I go any further. Now, these next two, show me this page just a little bit so we can see them both clearly. These next two are a little more complicated looking than just a straight p-series or a geometric. You notice the bottom one almost looks geometric, but you have that +2. And this top one has got a lot of other pieces added to it. On this particular one, I would compare on these, and I would want to compare this numerator one to the square root of n cubed over n cubed, and that's because this will always be less than or equal to my sequence here that I have here. The series will always be less than or equal to the square root of n cubed over 3n cubed. Okay. This bottom one I would compare because this is always going to be less than or equal to 1 over 3 to the n. So both of these are comparison tests. The next type I have is this one, and Alternate series ones are really obvious because you're going to see something that is going to make it alternate. And in this case, the moment I see that -1 to the n, it tells me I want to look for alternate series tests. Some other ones that will also alternate could be -1 to the n plus 1 or n minus 1. You could also, if you wanted to be super fancy, have like some cosine pi n. That's another fancy one that will alternate as well in it. The next type I have here, I've got the sum from 1 to infinity of 2 to the n over n factorial. N factorial is kind of a tricky one. You can't use the integral test on it because we don't know the antiderivative of things with factorials. So the clue that I use for that is to use the ratio test. So ratio test works really well with things that have powers on them and also with factorials. It's excellent with factorials. And then this last one I have here, I have n(e to the negative n squared. I look at this and I see something that I can do the integral of. And so I would go for the integral test. Come on. And that, when I go to do that integral, we would have x e to the negative x squared, and I would go from 1 to infinity. So as t approaches infinity of this improper integral. And this is a u-subbable integral, so it's kind of a nice, and then we have dx. Okay. And that concludes this video on approaches to solve problems. Okay, hope this helps.